This week, we're going to be looking at clustering. Specifically, we're going to be looking at a data set where every row of the data is how many bikes were rented in London for a given hour. Well, we're going to be using that to identify hours that are similar, hours that might be rainy, hours that might be nice, across the entire data set. This is how we will build our clusters that we'll use to explore bike rentals. First and foremost, you'll see this is the actual data that's being loaded in. I have copied this data set, so if you go over to Kaggle, you can see where the data set came from. I've copied it onto our web server just to make sure that it's always available. And we'll go ahead and set this random seed so that you get the same types of data that I get. So I'll go ahead and run this and load in the data. Now, the first thing I want to do is just take a quick look. Let's see how big our data frame is and take a look at the actual data. So around 17,000 hours of data within this particular data set. And let's just take a look at the head of this data set. Okay, so here's our data. We have a timestamp, which is representative of the hour that the data was recorded. So this row, for example, means on the first, I believe the first day or the fourth day of January in 2015, there were 100 within the first hour. So that would be from midnight until 1 a.m. There were 182 bikes that were rented across the city of London. T1 is in Celsius. This is the kind of actual temperature. T2 is the feels like temperature. Humidity is how humid it was, wind speed, weather code. I believe these are higher values indicate worse weather. Is holiday is a binary, is weekend is a holiday, and then season is 1, 2, 3, or 4. So again, the question is, can we figure out, are there groups of days that are similar? What defines those different groups? And once we've defined those groups, can we figure out what is distinguishing busy days from less busy days, the busy group from the less busy groups? Let's go ahead and start digging into this. So first and foremost, we're not going to be doing any kind of like temporal modeling, so we don't actually want to retain this timestamp. But one thing we do want is to extract information that might be useful. So one thing that we can do is say, okay, what is the hour of the day? So, we want every single row to actually have an hour of the day that will range between 1 and 24. So we'll create that quickly. All right, and there we go. So what we've done here is we've gone in, we've created the new hour of day field, we've removed the timestamp column, and then just printing this out. So you can see now we have the hour of day, which is going to come from 0 to 24. This will allow us to cluster based on the hour of the day. I mean, I think it's entirely plausible to believe that the count of bikes that are being checked out from somewhere is likely to have there's going to be some importance in terms of the hour of the day when those different counts will come out. So we do want to include that information. You could, of course, define this more broadly. You could, for example, create a morning, afternoon, early morning, evening binary, or binary variables, or even a classed variable. But for this, I think this is a quick and easy way to do it. Now what we actually need to do is create just kind of a brief visualization of the relationships within our data. We want to get an idea of what we're working with, and this will take just a moment to produce. All right, and there we have it. So this is now a diagnostic plot. What we're looking at here is the scatter plot for every single variable in our data frame against every other data frame. So like, for example, this scatter plot in the first row right here, this would be the scatter plot comparing count, which we see here on the y-axis, against T1, which we see down here on the x-axis. So this is the scatter plot between count and temperature. This would be count in the feels like temperature, humidity, wind speed, so on and so forth. So this on the diagonals also shows us the distribution of our variables. So you can see the count, for example, here. This would be count here and then count here. This is actually showing us the distribution. So we see there's a lot of hours where there's very, very, very small numbers of bikes being checked out. And then there's a tail where you get kind of a bigger and bigger, where you get less and less frequently. You see small, very large numbers of things being checked out, but it's fairly uncommon. The vast majority of our data is relatively small numbers. So this type of a chart gives us an idea of what kind of thresholds that we might be able to observe in our data. But more importantly, it allows us to look at things like multicollinearity. Do we believe that some of our data is tightly correlated with other elements of our data? Looking through this, the answer to that question is immediately yes, right? If we look at T1 and T2, so this is the true temperature and the feels like temperature, we have very, very clear correlations in that data. So there's not much new information in the feels like temperature when we contrast it to just the true temperature. There aren't any other extreme examples like that, but there's certainly patterns there. Hour of day also has very clear cyclical patterns when it comes to temperatures. Just as an example. So we do see some other types of correlations in our data, but the most clear one is these T1 and T2. Now I'm going to go through how we created this diagnostics chart. So just very briefly, first, we're selecting only numeric data types from this particular data frame. Then we are going in and we're creating the scatter matrix. So this is a pandas function that allows us to create a scatter matrix. All we have to define is the relative transparency, the figure size, and then what we put on the diagonals. So this diagonal equals KDE is why we have the histograms on these diagonals, a title, and then show. So this is a fairly straightforward set of commands. One thing that we can do to make our task easier in the case where we have some multiclinearity and there just looks like there's other data that might be measuring similar things, is we can do what's called a PCA. We can actually reduce the data down to 2 dimensions that tries to capture all of this information in just two columns of data. And so we are not going to go into, in this course, the nuances of PCA, rather we're just going to leverage it. But the fundamental idea is that we're going to retain as much explanatory capability as we can from the data, but reducing it down instead of having 10 variables that we're looking at here that might have some redundancy, reducing all of this down into just 2 variables that have as little redundancy in the information as possible, or no redundancy in most cases within PCA. Let's go ahead and do that. We'll go down to a new setup here, and the first thing we'll do is we're going to select only the numeric entries in our data frame. This is the code that will actually produce our PCA. So as you can see here, we've gone through and we've added to our data frame 2 new columns of data. So just to very briefly talk about what happened here. First, we did our normal scaling. I'm not going to talk about this. We've done this before. We created, make sure all of our values were actually scaled. But then what we do is we run this PCA where we are requesting that we get 2 components back. So what this is going to do is it's going to say, okay, across all of these variables, count T1, T2, humidity, wind speed, so on and so forth, what are the 2 pieces of data that we can create that best represent all of these values? So let's take a look at this data. We now have PC1 and PC2, which again, the goal of these 2 variables is to summarize kind of all of these other dimensions of data. So let's create a scatter plot. And there we go, where all the S did here was change the size of the points because there's a lot of points. So these components is what they're called. They're not very easy to interpret, but what the important thing here is that a point over here is very likely quite different from a point over here. That is, the data that is being summarized by the component 1 indicates that there's something very different about these points on the left-hand side as contrasted to the points on the right-hand side. Similar up and down, right? There's something very different about these points down here at the bottom as contrasted to those points up here at the top, just based on the data. We don't know what those differences are at this point, so we will explore that later on, but this does provide a meaningful way to look at what those differences are. Our goal now is to look across all of these points and establish clusters. Where are the clusters of points that are most similar to one another? And so we're going to look at that using a lot of different approaches. Now, for the sake of our sanity, we are actually going to be using a sample of these simply because there are so many points here. It's very, very hard to see what's going on, and it will also take a very, very long time for our cluster models to fit. So let's go ahead and do a sampling. What we've done here is we have first taken a sample of 1,000 of the points in our original data frame. So that's what's represented on the second data frame the second scatter plot down here. We have then defined a new data frame called XPCA, which only has the information on the two components. So we just have two columns of data in XPCA. This will make it easier to fit our clustering models later. We have removed from our X sample, so those 1,000 rows, PC1 and PC2, and we'll be going into why we remove these later. And then all I've done is I've plotted the new data set at the bottom. So this is the sample data set down here. And you can see it's much more sparse, but maintains similar patterns. You can see there's kind of more points in the middle region in both cases, so like more points around here. There's a little bit more density. Similarly, when we sampled, there's more points down here. Because the sampling is completely random, we should expect to see reasonably similar patterns. Let's go ahead and do our first clustering algorithm. And just as an example, we're going to go through this once with what's called spectral clustering. So we'll go ahead and type in that code now. All right, so here we go. So now we have, this is the visualization of our spectral clustering model. And we'll go into more detail on how spectral clustering works in class. But what you're seeing here, so first we went ahead and we fit our model. So our spectral clustering model, in this case, we have to define the number of clusters that we would like the algorithm to give us. So in this case, we're saying give us 3 classes that have the most kind of internal cohesion possible. The affinity in this case is how it's defining what neighborhoods are, and we'll talk about that more in class. And then nearest neighbors, again, this is for the spectral clustering algorithm, how many points it's considering when it looks through, when it runs its algorithm. Additionally, for every single one of these, we will be doing this. So we're actually going to go through and we're going to do a visualization of what these clusters look like. So here we have these components, and basically what happens is we're saying, okay, all of the points over here on the right, these purple points, these are all going to be similar. They're all in a similar class. All of these blue points are in a similar class. All of these yellow points are in a similar class. And effectively what that means is that according to our data, these points in yellow are all generally similar. There's something similar about them. We don't know what is similar about them at this point, but we know there's something similar about them. Similarly, all of the points in purple and all of the points in green. So put in, plain English, this means that an hour, let's say one of these purple dots is an hour of the day in January. This purple dot next to it, like this purple dot right here, and then this one of the ones next to it would be an hour of a day in May. Those 2 hours of the day are similar in terms of all of the measurable data that we have. So we do want to answer the question, okay, these groups, why are they being determined as similar? What are the characteristics that are driving these clusters? So once you have your clusters, we can actually go and we can use a more common model that you have already implemented in terms of a classification tree to try to understand how these clusters are being constructed. This will make them more interpretable. So this is how we're going to go about that. And here we go. So what have we just done? First, we just refit the model. So these are the same lines that we had above. Then we save into a data frame the results from that model. So we save the PCA information, the XPCA information. We create a new column and we call it cluster. So that's what this data frame is. So we effectively have 3 columns of data in this data frame: PC1, PC2, and then the cluster information. So that adds that all in there. Then what we're doing here is we're actually going to fit a decision tree classifier based on this information. So we're going to have we're going to fit based on all of our X covariate information. So this is our X sample values. You'll remember all the way up at the top, this includes count, T1, T2, humidity, wind speed, so on and so forth. So what we're going to be doing is we're going to predict what class a point belonged to, 1, 2, or 3, based on count, temperature, humidity, wind speed, weather code, holiday, weekend. That will let us know what the predominant things are that define each one of these classes. So that's what this decision tree does. This is the same logic that we used from last week for our decision tree classifier, so nothing at all has changed here. All we're trying to do is identify what are the most important drivers. So basically, right now, here, we're in component space. This is those kind of reduced form components. We're translating that into real space. This is kind of the real dimensions, the real values that we're interested in. So first and foremost, the first split that we see is this T2. So this is the feels like temperature. So in cases where it feels cold, that is, it's less than 13.25 degrees Celsius, we go to the left here. Then, in cases where the season is less than 2.5, so that means it's winter or spring. That's true. If that's true, we're going to go to the left here. And what we see in this node is the class is going to be predicted as class 0. That is, if we look at these, that there are if we do these splits, there are 146 cases that are summarized as class 0, 54 that are class 1, and then 104 that are class 3. So there's some mixing here, but overall, this describes a day that belongs in class 0. So if we scroll back up here, class 0 is in purple. So this is a day that is one of these dots. It's a member of one of these clusters, or it's a member of this purple cluster. Let's take another example. So if we do the same thing, so let's say temperature is less than 13.25 degrees, but the season is either summer or winter. So then we go this way because that's false. In that case, all 258 of the points are going to be a member of class 0, and 2 are going to be a member of class 3. So in this case, we can say with some pretty high degree of confidence that class 0 is defined, one very pure member of class 0 is the cases where it is cold in the winter or fall. So we have fall or winter and it's cold. That's what these purple cases are. Here it would be cold days. So if we go the other way, right, from true, 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 these are going to be cold days in the spring or the summer. So everywhere here is cold days in the spring or the summer. This is cold days in the winter. So what do we learn about class 0? Class 0 is generally being summarized. It's summarizing cold days. Everything here is a cold day. Additionally, we see another split in the data here, which is this is going to be warmer days when the temperature is not less than 13.5 degrees. And then there's a split underneath that, which is count. So this is the number of bike rentals that are being that are had. And so there's another split here, which we see let's look at this one first. So this would be class 1. Almost all of these observations are class 1. So these are cases where there were more than 718 bike rentals and it was a relatively warm day. So that's what this terminal this is. So warm day, lots of bike rentals, that's class 1. So back up here, we see that all of these green dots in the upper left-hand corner, these are all members of class 1. So these are cases where there were a lot of bike rentals and it was relatively warm. We can do the same thing for class 2, right? So we look here, so here's class 2. This would be relatively few bike rentals, but it was also warm. So we can learn that about class 2. That's what that definition happens to be in this case. So all these yellow dots. So that lets us kind of break down, okay, what the differences is for this clustering. So these are, if you just look at the data, the most clearly defined differences are between cold days, first of all. So we have all of these cold days. And then we have warm days on which there are some warm days where the bikes were rented a lot and some warm days when the bikes were not rented a lot. So we can already start to define, things that matter. It matters what the temperature is. What we're not seeing here is like holidays. Holidays don't seem to matter at this point. So we have some questions that we can start to ask. Some interesting questions like, why on some warm days do you see a lot of bike rentals and why on some warm days do you not see a lot of bike rentals? On cool days, what are the average number of bike rentals like? How different are they from warm days? These are questions that would likely be meaningful to ask because of how these clusters have fallen out. In the next video, we'll look at exactly this and look into how we can analyze this approach using use this approach using a lot of different clustering techniques.